Hello, class. So in this video, again, we're still on section 3.2/4.1. In the previous video, we talked about linear dependence and linear independence, and we went over an example of how to show, well, two examples of how to show whether, in this case, we did show that these functions were linearly dependent on the interval -pi/2 to pi/2. In this example, we showed that the functions sine x and cosine x are not linearly dependent on any interval, which means that they're linearly independent. Okay. So as I mentioned, I want to do one more. So find an interval on which f1 equals x and f2 equals x squared are linearly independent, which again, I'm going to abbreviate Li as linearly dependent. I abbreviate by LD. Okay. So again, you always start with the same equation. Always start with coefficients times this function, so a linear combination of these functions equal to 0. Now, for the linear independence, we need to show that the only way this is true for all x on whatever interval we're looking at is if both coefficients are 0. Right? So we need to show that the only way this equation is true, so star, right, is true for all x on some interval, is if all of the coefficients are 0. So C1 equals C2 equals 0. Okay. So for linear dependence, you always started with this equation and trying to show this. Okay, so you saw it in the previous video. I'm not going to go over again. For linear independence, you start with the same equation, but you want to prove something a little bit different. You want to show that, in fact, the only way this is true for all x in an interval is if the coefficients are both 0. Well, just as before, we can do some rearranging of this equation. So let's subtract, for example, C2 times x squared from both sides. And again, I'm going to ask you, is it possible for these two things to be true on some interval without both coefficients being 0? And again, you can show this is not possible because you can look at the graphs. For this purpose, I'm just going to draw the graphs of where C1 equals C equals 1 and negative C2 equals 1. But it's going to be the same idea because you have one function like this. That's obviously x. You have another function like this. That's, should cross the origin. That's obviously x squared. Right? So no matter what choices for C1 and C2, and actually let's include the negative. Let's do it like that. Okay. So it doesn't matter what choices you have for C1 and C2. Remember that when you're multiplying a function by a constant, the only two things you can do are either stretch or compress vertically or reflect about the x-axis. Oh, shoot. I didn't want to do that. I wanted to draw a reflection thing. So look at these two graphs. Is it ever possible to stretch or compress them vertically or reflect them about the x-axis in a way such that they are equal on some interval? Again, you can see that they're equal for particular points, right? They're obviously equal at x equals 0 and x equals 1. But those are specific points. An interval contains infinitely many points. Right? So an interval of the form -1 to 1, for example, contains infinitely many points. So again, convince yourself by looking at these graphs and thinking of what those specific transformations look like. These things are only ever going to intersect like this in 2 points. They're never going to intersect in an interval. That means that the only way this is true, the only way these two functions are true, this equation is true on an interval, is if C1 equals C2 equals 0. Right? The only way this is true, right? This equation. And this works for all x for any interval. Right? Doesn't matter what interval you choose. The only way this equation this asterisk symbol is true is if both the coefficients are true. So this works for any interval I. So by definition, these functions are linearly independent on any interval. Doesn't matter which interval you choose. Okay. Now that's the last example that I'm going to do in class in terms of using the actual definitions of linear dependence and linear independence. Because now I'm going to make your lives amazing because I'm going to give you a way to do this without actually having to use those definitions. I mean, it comes from those definitions, right? So it is here somewhere. It's just not something you're going to have to do directly. Okay? So first, I have to introduce this new symbol. Suppose that you have functions f1, f2, up to f sub n. So you have n functions that possess at least n minus 1 derivatives on some interval I. We define the Wronskian, so it's a weird word, but Wronskian, of these functions, which we're going to denote w of whatever functions we're working as, like that. And by definition, it's going to be equal to this. Now, this is meaningless to you right now if you haven't taken linear algebra or worked with matrices. So I'm actually going to have to do here at this point a little bit of introduction about how matrices work. It's just going to be very small. We only need a small part. But basically, this is what it is. If you have n functions, you need them to be at least n minus 1 differentiable on some interval. Right? That's the first thing you need. And then you can calculate this thing, which I'm going to show you how to do. Okay. So for example, if you have 5 functions and you want to compute their Wronskian, you need them to be at least 4 times differentiable on some interval. If you have 8 functions and you want to compute their Wronskian, they have to be at least 7 times differentiable on some interval. Okay? Meaning that you can take the derivative 7 times. So let's do a little bit of introduction to linear algebra, or just working with matrices. Now, this rectangular array here, which is actually a square array, so this square array that we have with vertical bars, that's what we call a determinant of a matrix. Okay. So we first have to start introducing what a matrix is. So I talked a little bit about this on the Mathematica help video, but since I'm not sure if you've seen that, then I'm just going to introduce this again real quick. I didn't introduce everything exactly, so I'm going to make it precise here. Anyways, okay. So what is a 2 by 2 matrix? A 2 by 2 matrix is just a 2 by 2 array of numbers. Doesn't necessarily have to be numbers. They can be functions. They can be other things. So in general, a matrix is just a 2 by 2 array of anything enclosed by square brackets. Right? So for example, this is a matrix. Oh, and this 2 by 2 means that you have, so the first entry means the number of rows, whenever you see this notation, and the second number means number of columns. So specifically, a 2 by 2 matrix is a 2 by 2 array of numbers enclosed with square brackets. You could have a 5 by 5 array, a 10 by 10 array, a 17 by 14 array. In our case, we're only going to be working with square matrices, meaning that the number of rows is set the same as the number of columns. Okay. So for example, this is a 2 by 2 matrix. This is a 2 by 2 matrix. Notice the only thing that's changing is the things that I'm putting into the array. Okay. Again, in most of the things you do, they're either going to be functions or numbers. Now, that's it. That's what a 2 by 2 matrix is. How do you compute the determinant of a matrix? Well, this thing here, as I mentioned, when you have a matrix with vertical bars, that is telling you to compute the determinant of that matrix. That's what it's saying. So how do you compute the determinant of a matrix, which we denote by either writing the matrix or just the name of the matrix, always now enclosed, not in square brackets, but in vertical bars. How do you compute that? Well, you use this formula. You multiply the diagonals, so multiply AD and subtract the product of the other diagonal. So subtract b times c. And that's it. That's all we're going to need to know about matrices. So, for example, let's calculate the determinant of A, where A is the matrix 1, 2, 3, 4. So by definition, the determinant of A, which you can also denote as the matrix, but replace the square brackets with vertical lines. How do you compute it? Take the product of the diagonals. Right, so in this case, multiply 1 times 4. It's like 1 times 4. And subtract the product of the other diagonal. So multiply 3 times 2. So minus 3 times 2, which is what? So 1 times 4 is 4. 3 times 2 is 6. 4 minus 6 is negative 2. As simple as that. Now, there are ways to extend this to larger square matrices. So 3 by 3, 4 by 4, 10 by 10, n by n in general. But in this class, we're only going to do it by hand when it's a 2 by 2 matrix. I will show you how to do it on Mathematica when it's an n by n matrix. So you might have to do that in the homework, but again, in class and in exams, we're only going to do it with 2 by 2 matrices to save time. Because the formula for even the 3 by 3 one starts to get a little bit complicated. Okay. Now, let's do another example. Now that we know how to find determinants, and given that we know that to find the Wronskian of a set of n functions on an interval, what do we need? We need them to be at least n minus 1 differentiable. And what do? You create this matrix where the first column starts with the function, then the function's derivative, up to the nth minus 1 derivative. That's why we need them to be at least n minus 1 differentiable. The second column is the second function, then its derivative, up to the n minus 1 derivative. And in general, the number of columns you're going to have is the number of functions that you have. All right, so the last column is going to be the nth function, followed by the nth derivative, but the first derivative, all the way up to the nth minus 1 derivative. So that's how you find the Wronskian of a set of functions that are at least n minus 1 differentiable on some interval I. Okay. So let's go ahead and apply it. Find the Wronskian of x and sine of x on I equals negative infinity to infinity. Okay. So we have two functions. It doesn't really matter in what order you put them in the matrix. Right? So you can just call the first one f1 and the second one f2. We have two functions, so we need them to be at least 1 times differentiable. Okay. So, well, x and sine of x, we know that they're 1 time differentiable. And on what interval are they 1 time differentiable? Well, everywhere, right? The derivative of x is 1, which exists everywhere. And the derivative of sine x is cosine x, which exists everywhere. That's why we can calculate the Wronskian on the whole interval. So basically, this interval I on which you're computing the Wronskian is usually just going to be restricted by at what intervals are your function either differential, how many times differentiable you need, or also by the domain, like are the functions even defined in this interval. And so those are the two things that are usually going to restrict your interval on which you calculate the Wronskian. Right, so usually restricted by on what interval or balls, so S, are your functions. So if you have n functions, you need n minus 1 derivatives for each function. So I'm just going to write are your functions n minus 1 times differentiable. And what are the domain of your functions? So if they're not even defined, then you can't, it doesn't even make sense to work with them. And the last thing, actually, that I want to mention, that is kind of included in the domain of functions, but it's bigger, is the interval of definition of the solutions. Because for our purposes, we're going to be wanting to know the Wronskian of functions on whatever interval they are solutions. So the interval of definition, or the shared interval of definition, right? Because each function can have its own interval of definition, but we want an interval of definition that works for all of them. So interval of definition that works for all of them. I'm just going to say shared. So those are the things that are usually going to restrict whatever interval you're calculating the Wronskian in. In this case, since these are not necessarily solutions to differential equation, there's no context. All we're interested in is the first two. Are they differentiable? We have two functions and we only have to check for one derivative. So are they one differentiable everywhere? And are they defined everywhere? Okay, they are, so we can calculate the Wronskian for all real numbers. Okay? So by definition, the first column is the first function and its first derivative. The second column is the second function and its second derivative, its first derivative, so cosine. So this is the matrix. And the Wronskian then, which again you write w of your function, so w of x and sine x, is given by the determinant of this function, of this matrix, sorry. So the determinant of x sine x, 1 cosine x. So now we can calculate because we have a formula. Just multiply the entries in the first diagonal. So if we do that, we get x times cosine. So x times cosine. And subtract the product of the entries in the other diagonal. So the other diagonal is 1 times sine. Right? So we simplify, this becomes x cosine x minus sine x. So that's the Wronskian. Now you might be wondering, why is this useful? I mean, okay, I know how to compute this thing, but why? Well, the reason why is because computing the Wronskian is exactly how we're going to tell whether functions are linearly independent or linearly dependent on an interval. Okay? So I'm going to do that on the next video.